Hello everyone, this is the second part of the lecture on elasticity and regional isostasy. So previously we've discussed flexure, and in particular we mentioned some examples where the local isostatic model cannot be applied. So there was the case of the subduction zone where the plate, an elastic plate, is being bent, which is leading to an outer rise. In the case of Seamonth, we have bulging of the plate away from the loading. And in the case of Lacolith, we also want to explain the deformation of the plate below the magma, which is being emplaced within the crust. So for all of these models, we need to design another model than the local isostatic model, and that's the regional model that will require defining a rigid plate. On the way to this, we have studied the relationship between strain and stress in a small strain elasticity framework. So we've defined the strain, the infinitesimal strain tensor, the stress tensor, as well as the constitutive relation that links the stress to the strain. This is the big D tensor, which for the case of linear elasticity can be written using the Voigt notation as a matrix here. So that's the relation between the components of the total stress tensor and the components of the total infinitesimal strain tensor using these coefficients. During the exercise, you were led to manipulate these objects, and one of the questions were to use the constitutive relation here and to derive the relationship between epsilon yy and epsilon xx and the relation between sigma xx and epsilon xx. So these steps you've already derived, and that's a first step towards the flexure equation. So now we want to quantitatively study how a plate bends when a load is applied on top of it. So we're going to look at this sketch now. This is the plate, and in between here you see one small element of this plate. This small element spans from x to x plus delta x. So that's the size of the element along the x-axis. And there are different quantities here, and these different quantities are different types of forces and moments and pressures. So first, I should introduce the deflection. So the deflection is basically the quantity along the y direction by which the plate is deflected. This is the amount of deflection. So you see a large deflection W here and a smaller deflection W plus a change of W. Then there is a pressure. Q is a load which is applied on the plate. It will have to be integrated along the length of the element here. P is acting along the x direction. It's a horizontal force. V is acting along the y dimension. This is a shear force. And M, here and there, are bending moments. So in the next slides, we will go for a derivation of the flexure equation in less than 10 steps. And it's basically taken out the third chapter of the book Geodynamics, which I advise you to check out. Also, most of the illustrations are taken from these books. So all the illustrations that do not feature any specific reference come from the book Geodynamics. So step one is basically the force balance in the vertical direction. So let's review the forces acting vertically. So there is one force acting upward. This is V. Forces acting downward. There is V plus dV on that side, there is Q times the length of the element. Remember, this is a pressure, so we need to multiply it by the length of the element to get the integrated effect of Q. So that's going down, down, and this is up. So you can solve for dV. So dV is equal to minus Q dx. And this equation, you can divide the left-hand side by dx, and you obtain dV dx equal minus Q. Next, we need to compute the net torques which are induced by the bending moments and the different forces into play. So let's start with the net torque induced by the bending moment M. So we have M on that side and M plus dm on this side. So if you take the net, which is basically the difference between this and that, you obtain dm. So this is the net torque induced by the bending moment. Then we have the shear force. And this is a clockwise moment. You can already imagine that the sense of motion is this way. We can compute it by multiplying V by the position. So that's a torque, and the net torque will be the difference with the product of V times x plus delta x. So here we assume that dV is negligible for the net torque. So Vx minus V times x plus dx is simply V dx. Then comes the effect of the horizontal force. So we have P, which is now acting horizontally. It will act in the middle portion of the plate. The vertical position of this middle portion is W on that side and W plus dW on the other side. So the net torque is P times W for this side minus the contribution from that side, which is P times W plus dW. This gives us a net torque of minus P dW. This is a counterclockwise torque. So if you make the balance, we have the clockwise and the counterclockwise contribution. This gives V dx equal dm minus P dW. Once again, you can divide everything on the right hand side here by dx, and you will obtain this equation. dm dx is equal V plus P dW dx. So this equation we have to keep in mind for later use. In the next step, we are going to combine equation 1 with equation 2. First, we start by deriving equation 2 with regard to x. This leads us to a second order differential equation of that form. And you can recognize the term here, dV dx, for which we know this equation, equation number 1. So we can substitute dV dx by minus q. And this leads us to this equation. So this equation is a second order differential equation which relates m, w, p, and q. That's already a very important part of the job we have to do in this lecture. So it's quite some effort, but there is much left to do. Step number 4, we want to express sigma xx as a function of epsilon xx. Luckily, this was already derived as part of the exercise of the previous session. This is the solution. Sigma xx is equal to E divided by 1 minus nu square times epsilon xx. So this part was already obtained, and to reach this, you had to manipulate the constitutive relationship and following the different hints which were provided previously. So that's given for free. So let's jump to step number 5. In step number 5, we want to relate the bending moment m as a function of epsilon xx. So we want to relate bending moment to horizontal strain. So the bending moment is the integral over the plate thickness, so from minus h divided by 2 to h divided by 2, h being the plate thickness, of sigma xx times y dy. And we also know that sigma xx has this expression, which was derived before. So you can substitute this expression into this integral, and this gives you the expression of a bending moment as a function of the horizontal strain epsilon xx. This is step 5. Now, step 6. We want to relate the horizontal strain epsilon xx to the coordinate y. For this, we will use small angles. So basically, we will assume that angles are small. So if phi is a small angle, phi is approximately equal to sinus phi. That's another sketch here where you see a plate element which has been strained, leading to a delta L, which is a displacement. So L is the length of the element, and delta L will be a deformation. And you see that this deformation varies along the thickness of the plate. So we have this radius here and this opening angle, phi. And phi can be approximated as L divided by R. Once again, L is here and R is this length. That's using the small angle approximation. Then we have this angle, phi, which is also found on that side, and which can be approximated by delta L divided by y times minus 1, because there is contraction for positive y. Then we can express phi as either minus delta L over y or L divided by R. So you can also express delta L. Delta L is minus y times phi or minus y times L over R. And this leads to the expression of epsilon xx, which is equal to minus delta L over L or y over R. So we now relate epsilon xx to the coordinate y. Step number 7, we want to relate epsilon xx to w. So that's another sketch here. You see again L, the length of our element, which is being curved. There is the angle phi here. And you see that at coordinate x, there is an angle, a local angle that can be measured here, alpha. And as the angle here increases, the angle to the horizontal will increase. So on that side, the angle is alpha plus d alpha. There is an increment of the angle along the length of the element. So the element length, dx, is close to the length L. That's one of the first things. These are small lengths. Then a second thing to keep in mind is that since alpha varies with x, we can relate alpha to dw dx. But we take a minus sign here because as you can realize here, alpha increases as W decreases. Then there is this increment of the angle, d alpha, and here you can notice that d alpha is simply equal to phi, this angle here. So using small angles and the assumption that W and L are small, we can come down to these expressions. So this is what to be kept in mind. And now we have also phi, which is equal to d alpha. So let's express d alpha as d alpha dx times dx. And now we will substitute d alpha dx by dw d2w dx2. So you see the derivative of alpha with regard to x is the second derivative of this. So phi is minus d2w dx squared times dx. Then we are going to take dx to the right hand side. So we will divide phi, the angle, by dx. And this will be simply equal to that term. But we should also remember that dx is close to L. So you can also write that this is equal to phi over L. And if we remember from the previous slides, phi is also equal to L over R, or minus delta L divided by Y. So we will use this to substitute there, and we get the result that this is equal to 1 over R. Now we should recall the definition of the horizontal strain. Remember that the horizontal strain came down to be equal to y over r. So we will simply combine the two expressions, and we obtain the result that epsilon xx is equal to minus y times d2w dx2. This is step 7. We're getting closer. There's still a little bit of effort to make. So step 8. Now we want to compute the final expression for the bending moment. So remember, we derived this expression before. Bending moment as a function of the integral of the horizontal strain times y dy. Now we introduce the expression for epsilon xx that we derived just before. So we use this now. We will substitute minus y d2w dx squared into this expression. And this will simply lead, this will lead to this expression. M is proportional to the integral of y squared over the plate. So now we can integrate this equation. The integral of y squared is y to the power 3 divided by 3. To solve for the integral, we need to use the two bounds. So we will need to evaluate y3 over 3 at plus h over 2. And we need to subtract the value of this, evaluate it for h, for y equal minus h divided by 2. This leads to these numbers, and this is equal to 2 times h cubed divided by 24, which is simply h cubed divided by 12. That's a very important equation now, because we will now introduce one of the main parameters of the flexure model, and this is the flexural rigidity. So let's take the factor 12 to the front of the equation. So it ends up here. So we have this parameter EH cubed divided by 12 times 1 minus nu square factor times minus 1. This thing here will be defined as D, the flexural rigidity. And there is a thickness inside this expression, H. And this thickness, in the context of lithosphere dynamics, we will relate it to the elastic thickness of the lithosphere, TE. This we'll discuss in more details in the next lecture. So this will be a very important geometrical parameter inside the expression of D, because it is taken to the power 3. Now we reach the final step in the derivation of the flexure equation. We have the definition of flexural rigidity. And we have this expression, a second order differential equation that relates M, Q, P, and W. We now want to combine these together. So we will use the definition of the moment, which is already a second order derivative of W. We will substitute this into this equation. And this will lead to a fourth order differential equation, because you take the second order derivative of a second order derivative. So this is D, big D, D to the power 4 of W dx to the power 4 is equal to Q minus P D2 W dx2. So that's a fourth order differential equation that we will need to integrate in order to find the unknown W here. That's actually it looks complicated, but it will be very handy. So we will solve for example, the loading of an oceanic lithosphere due to a seamount, or the flexure of a plate due to subduction, using this equation here. The only thing that will change between these different models will be mostly the boundary conditions or the shape or nature of the load which is applied to the plate. So that's already very promising. We derive now this fourth order differential equation, and I think we can already call it a little success, because it was a lot of effort. So once again, the master equation looks like this, and inside there is a very important parameter, D, and D is a parameter that combines both strength, or I'd say Pascal unit, like modulus coming from the elastic matrix, E and nu, but also the thickness. So it's a combination of parameters that will be used to estimate the strength, so, or the rigidity of the plate. And the unit of this is, of course, Pascal times meter to the power 3. So it's Pascal meter cube. Then the next parameter is Q. And Q is a force per area, so it's a pressure. It has unit Pascal. Next comes P. P is the horizontal force per unit length. It's Newton per meter, or Pascal times meter. And last but not the least is W, that is featured on both sides of the equation here. And this is the deflection. So that's the unknown that we want to compute. It has unit meters. We will then apply this equation to, for example, compute W. You see it already on that sketch. That is giving you the magnitude or the height of the outer rise of a subduction. Or here the W gives you the deflection of the crust when magma is being injected inside the crust. So, as a summary, we've combined elasticity, force balance, and torque balance together to derive the flexure equation. This equation relates important quantities that will modulate the shape and the magnitude of deflections. The main parameter in this equation is flexural rigidity. And this equation altogether, since it's a fourth order differential equation, it will need a certain number of boundary conditions, but by applying this boundary condition, we'll be able to obtain values of W. In the next lecture, we will make some solutions of this equation. So we will see some solution strategies, and we will start with application of regional isostasy. Thanks for your attention.